Greetings. So welcome to today's class. So just a quick recap of what we were learning in the previous class. If we recall, we were looking at the notion of equilibrium states, and we figured out that for linear systems, we could have equilibrium state of that class of systems to be either a unique equilibrium state or a continuum of equilibrium states, right, which belong to the null space of the state matrix. And for nonlinear systems, there is a third class of equilibrium states, which essentially is a set of multiple isolated equilibriums, right? So that's what we learned in the previous class. So we are now going to build upon this, and then we are going to essentially see, how we can now analyze the stability of an equilibrium state. Okay, so let's discuss that topic today. Okay, so what we are going to look at is the notion of stability of an equilibrium state. So what do we mean by stability of an equilibrium state? So this is another notion of stability. We had already looked at bounded input, bounded output stability. Now we are going to look at stability of an equilibrium state. Okay, so let's define that, and then we will just go ahead and see what is the equivalent criteria, right, for linear time gradient systems. So what is this definition of this notion of stability of an equilibrium state? So this is attributed to the Russian mathematician Lyapunov. So that's why some people will call it as stability in the sense of Lyapunov. But let me write down the definition very clearly. So an equilibrium state X star is stable in the sense of Lyapunov. Okay, so as I mentioned, this is attributed to the Russian mathematician Lyapunov. So that's why we write in this way. So this is typically abbreviated as ISL. Okay, ISL means in the sense of Lyapunov. Okay, at time t0. Okay, so an equilibrium state X star is said to be stable in the sense of Lyapunov at a time instant t0 if given any epsilon greater than 0, there exists a delta greater than 0 such that if the norm of xt0 minus x star, I will explain what this is. Okay, what is in a physical sense? Okay, is less than delta, then the norm of t minus x star is less than epsilon for all t greater than or equal to t0. Okay, so this is the definition of stability in the sense of Lyapunov. So let me explain what this is. Right? What this notion of stability is. Okay, so this notion of stability essentially means that if we are having an equilibrium state, and if we perturb the system from the equilibrium state by a small amount, let's say delta, right? That's what this means. Okay, so that means that we are perturbing the system from the equilibrium state from the small amount delta. Then subsequently, the system state should lie close to X star for all time. Okay, so if you look at the example of the simple pendulum, we sort of discussed that, like when we had this a simple pendulum, and when we consider this equilibrium state corresponding to the vertically downward position, right? If we perturb the pendulum from that position, we saw that the pendulum would oscillate around that position, and we would call that what is the equilibrium state as stable, right? Is it not? So that's what we are formally writing down as a definition. All right. So on the other hand, if we had a vertically upward pendulum and we perturb that pendulum, right? So what's going to happen is that that pendulum will just fall down, right? It's not going to remain around the equilibrium state. Okay. So that's why it is not stable. So now you get the what to say physical meaning, right, behind this mathematical definition. Okay. So we are going to only encounter this definition only now. Okay. Just to so I just wanted to write down this definition so that all of us are aware of the uh, formal definition. Okay. We are not going to go into the mathematical proof or derivation of the equivalent criteria. We are only going to use the criteria. Okay, so which I'm going to write down short, right? So this is essentially stability in the sense of now. So in addition to this, when perturbed, if the state tends to external as t tends to infinity, then the equilibrium state is asymptotically stable. Okay, so now we know what is meant by asymptotic stability. Okay, all right. So what is meant by that? Suppose, let's say we even go to the example of the simple pendulum, right? So let's say we have the downward equilibrium state. Okay, we tap the pendulum, right? So what's going to happen? The pendulum is going to oscillate around the equilibrium state, and ultimately, what will happen is that it will settle down in the vertically downward position, right? So because typically there is some air resistance or some other friction, right, which acts on the pendulum and essentially ensures that it settles down, right, at the equilibrium state. Okay, so that is what is meant by asymptotic stability. Okay, stability means, suppose you picturize a pendulum which we tap, right? And let us say we have a simple pendulum. This dashed line is the vertically downward equilibrium state, and then we tap it, okay, and then take it to this one. Let us say it keeps on oscillating forever, right, without friction. Okay, so that is stability. On the other hand, with friction, what is going to happen is that the magnitude of the oscillations will keep on reducing, and ultimately this will tend to the equilibrium state itself, right, which will be the vertically downward state, and that's when this system is said to be asymptotically stable. I hope the difference between stability and asymptotic stability is clear, right? Yeah. So these are the definitions. So we are only going to use the criteria for the two for LTA systems. Okay, so as I mentioned, we are only going to use the end result. We will not derive these criteria by proving certain mathematical results. Okay, so we are only going to use them, right? So what we are going to do is that we will consider x dot of t equal to ax. So while we are analyzing the stability of an equilibrium state, typically we only consider the unforced term, right? Why? Because of the definition of stability, right? Because in this notion of stability, what we are saying is that look, we will only consider the system, which is not subjected to any external input, right? So that's why we don't see the BU term, right, coming into the picture, right? So in this equation, so we only consider the unforced term, right, as the state equation is considered. Okay, that's why we are considering this a homogeneous vector field. Okay, there is no BU term. So what are the criteria for stability? The equilibrium state star, okay, any equilibrium state, right, for this system, okay, is stable in the sense of the okay, if and only if all the eigenvalues of A have non-positive real parts. So what does non-positive real parts mean? That is, the real part should be negative or it can be zero also. Okay, and but there's a condition, and those on the imaginary axis. So that is, if there are eigenvalues of the state matrix on the imaginary axis for which the real part is zero, if there are eigenvalues of the state matrix on the imaginary axis, they are what are called the simple eigenvalues. So if you recall what is going to be simple roots of a polynomial, that means they are non-repeating. So if you have non-repeating eigenvalues on the imaginary axis also, it's okay, right? So this is a big difference, right, between before stability and stability of an equilibrium state. All right. So please note this important difference. That is, when we have before stability, we saw that all the poles of the transfer function must lie in the Markov complex plane for before stability. And we saw what happened when we had poles on the imaginary axis, right? So when we had non-repeating poles on the imaginary axis, for certain inputs, the output became unbounded, right? So we called it as critical stability or marginal stability. And at that time, I told you that I will also provide another perspective of why that term is used. Now we look at why that term is used, right? Because what is happening is that if we use the notion of stability of an equilibrium state, if we have eigenvalues of the state matrix on the imaginary axis, and let us say they are non-repeating, and all other eigenvalues are in the left of complex plane, the system is still stable in the sense of Liouville. Okay, so it is not asymptotically stable, but it is stable. So you see that like this is something of a via media. All right, so that is it's not unstable, but it is just stable. Okay, that is if you have non-repeating eigenvalues on the imaginary axis. All right. So the second criteria is the following. Further, so this is the reason why some people will say, hey, look, even if you have non-repeating poles or non-repeating eigenvalues of the imaginary axis, the system is stable. Okay. So what they are not completely telling us, stable in the sense of what? Okay, it is not like Bibot stable, but it is stable in the sense of Liouville. So that's why like there's somewhere in between. So that's why people call it as marginal critical stability for these reasons. Okay, one reason for marginal stability is that as we know, if you have non-repeating poles on the j omega axis only for one class of inputs, the system output becomes unbounded, right? Reason number one. And if you have non-repeating poles on the imaginary axis or non-repeating eigenvalues of the state matrix on the imaginary axis, the system is still stable in the sense of Liouville, right? So those are some important points that we need to keep in mind. Further, the equilibrium state is asymptotically stable. Is asymptotically stable if and only if all the eigenvalues of A have negative real parts. So now we can observe the stricter condition, right, that comes with it. Okay, so we need all the eigenvalues of A to have negative real parts for asymptotic stability. Okay, so it is not only enough for no eigenvalue of A to be in the right of plane, but all eigenvalues of A should be in the left of complex plane. Okay, for the system equilibrium state to be asymptotically stable. All right. So the third criteria is the following. So if any eigenvalue of A has a positive real part, the equilibrium state is unstable. Then the equilibrium state is unstable. Okay. So this is an important result for LTA. So let me repeat once again. Like we are essentially looking at stability in the sense of Lyapunov or stability of an equilibrium state. When we are looking at stability in this sense, and we consider the unforced system x dot equals ax. When we are doing that, depending on the eigenvalues of the state matrix, we can have different criteria. Okay, that is the first result. So what do we mean by that? If all the eigenvalues of the state matrix have non-positive real parts, okay, that is, they don't lie in the right of plane, and those eigenvalues of A which potentially lie on the imaginary axis are simple, that is, they are non-repeating, then the equilibrium state is stable in the sense of A. Okay, that is criteria number one. Additionally, if all the eigenvalues of A have negative real parts, that is, there are no eigenvalues of A in the right of plane, no eigenvalues of A on the imaginary axis, then the equilibrium state is said to be asymptotically stable. Okay, so that is the second condition or criteria. The sort of corollary is that, like, if any eigenvalue of A has a positive real part, then the equilibrium state is unstable. All right. So these are the important criteria. Okay, as far as stability of an equilibrium state of a LTA system is concerned. All right. So let us do some examples to understand these aspects better. All right. But before we do an example, let me also write down a definition. I will write another definition. Okay. This is something which we already know as far as polynomials are concerned. So similarly, a matrix A or the matrix A is said to be full with if all its eigenvalues have negative real parts. Okay, so that is when a matrix is said to be. Okay, so if a matrix A is having all its eigenvalues in the left of complex plane, then that matrix is said to be a Fuchs matrix. Okay, so let's do a couple of examples, right, to understand this result better. Okay, so let's do an example where let us say first to begin with, we have a state matrix which is -2, 1, 0, and -2. Okay, so this is a state matrix A. So always when we have problems in the state space domain, the first task is for us to determine the equilibrium state. So what is this equilibrium state? How do we get it? We essentially solve Ax star equals 0. So in this particular case, what we do, the state matrix A is -2, 1, then 0, and -3. X star is going to be equal to x1 star, x2 star, okay, and that is going to be equal to 0 and 0. All right. So if we solve these equations, what are we going to get? We are going to get minus 2x1 star plus x2 star is equal to 0. That is the first equation. By multiplying the first row of the matrix with the column, we get that equation. Then we get minus 3x2 star is equal to 0. This implies that x2 star is 0, right? That's it. Okay, so from the second equation. Then if you use the first equation along with this, these two will imply that x1 star is also equal to 0. So consequently, our equilibrium state is the origin. Of course, we need not have done this calculation at all because we automatically know that since the matrix A is invertible, the only equilibrium state is the origin. But I just wanted to demonstrate it to you first, right? So that is the equilibrium state is the origin, and we have obtained it by solving the two equations, right? So obviously, we can infer from the size of the state matrix that we are dealing with a second order system, since the dimension of the matrix is 2. Now, let us calculate the eigenvalues of the state matrix. We solve the determinant of A minus lambda I equal to 0 to obtain the eigenvalues of the state matrix. So, what do we have? We will have determinant of minus 2 minus lambda 1, 0 minus 3 minus lambda is equal to 0. So this is the equation that we need to solve, correct, to figure out the eigenvalue. So if we now cross multiply, what we will have is minus 2 minus lambda minus 3 minus lambda is equal to 0. Okay, so because one of the off diagonal terms is 0, so this one. So we can immediately see that the eigenvalues are minus 2 and minus 3. That's it. Okay, so that's about it. Those are the two eigenvalues of the matrix A. So consequently, what we have is then the so-called spectrum of A. So if you recall, what is the spectrum of A? The spectrum of A is nothing but the set of eigenvalues of the matrix A will be minus 2 and minus 3. Okay, so that is the spectrum of A, and we can immediately observe that from the criteria that we wrote down, the equilibrium state is asymptotically stable. Why? Because there are two eigenvalues, and both eigenvalues are in the left of quadrant, right? So the equilibrium state is asymptotically stable. So that's what we can immediately figure out. Okay, so I hope it is clear how we got the eigenvalues, right, of the state matrix, and how we figure out that the equilibrium state is asymptotically stable. So once again, let me repeat the steps. When we are given a state space realization, the first task is for us to figure out the equilibrium state, okay, by solving Ax equal 0. Once we figure out the equilibrium state, we can determine the eigenvalues of the state matrix, and then they comment on the stability of the equilibrium state by applying the corresponding criteria. All right, so that's what we need to have. Okay, so now the next step, let us determine the eigenvector corresponding to the eigenvalues. So as the next step, we are going to calculate the eigenvector, okay, corresponding to the eigenvector.
Sir, one question about the spectrum of A.
Yes, please.
So is that does it have a different significance, or it's something like a different name to eigenvectors, eigenvalues?
So in matrix algebra, this is what is called spectrum. Okay, essentially that's a jargon which is used. Yeah, the terminology.
Okay.
All right. So in matrix algebra, when you talk about a matrix and we talk about spectrum of a matrix, it is nothing but the set of its eigenvalues. Okay?
Oh, okay, sir. Thank you.
Yeah,
Got it.
but of course this should not be mixed with the frequency spectrum that we have been studying, right? As far as signals are concerned, right? So,
Yeah.
okay, yeah. All right. So let's determine the eigenvectors. So if we recall the definition of eigenvalues and eigenvectors, so we need to solve AV equals lambda times V, right? So for that's the definition of eigenvalues and eigenvectors, but of course it's a catch that V is not zero. So this is a definition. So this definition gives us the equation that A minus lambda I times V is equal to 0, right? So this is the equation which we need to solve to get the eigenvector. Okay, so let's do that. So first, let us take the first eigenvalue and try to find the corresponding eigenvector. So let's first find out V1. Okay, the vector V1. The vector V1, let's say it corresponds to the first eigenvalue lambda 1, which is minus 2. So A minus lambda 1 identity times V1 is equal to 0. Now, if you look at A minus lambda 1, what will we have? We have A to be minus 2, 1, 0 and minus 3, right? That is our matrix A. Lambda 1 times identity is going to be minus 2, 0, 0, minus 2. Okay, just minus 2 multiplied by the identity. This multiplied by the column vector, let's say V11, V12. Okay, so those are the two components of the first vector, eigenvector. Okay, of course, I could have directly done the steps. I just wanted to illustrate how we calculate A minus lambda, right? For this, for all our information, right? So if you subtract the two matrices, what we are going to get is that like will be 0, 1, 0, and minus 1. Okay, so this is what we have. So essentially, we'll have V11, V12 is equal to 0 and 0. So this may look like an odd equation to begin with, right? So if you multiply the first row and the column, we get V12 to be 0, right? And if you multiply the second row and the column, we get minus V12 to be 0. So in fact, this is we don't have as many equations as sorry, we can't essentially solve for both V1 and V2, right? That is understandable because V1 belongs to the null space of A minus lambda I, right? So consequently, this is how it will come out. So we get one, what to say, component or a relationship between the two components, and then we need to figure out the other component, okay, in a general term. So we get that V12 is equal to 0. So consequently, V11 can be any scalar, which is a non-zero real number, right? So I'm sure all of us can understand it, right? So you put any scalar C, right, as V11, you multiply it by that matrix 0, 1, 0, minus 1, right, times T0, you will get 0, 0, right? So to just illustrate the point, so let us say we have 0, 1, 0, and minus 1, and C and 0. If you do the matrix multiplication, you will see you will always get 0, 0, right, irrespective of what value C is. Of course, C has to be non-zero, right? So that is why what we through this calculation, we can immediately conclude that the eigenvector corresponding to lambda 1 can be written as what is called the span of 1, 0. Okay, which is nothing but C multiplying the column vector 1, 0. Okay, where some C is some real scalar, it is non-zero. Okay? So that is how we write this eigenvector. Okay, so this is just a calculation of the first eigenvector. Okay, so what we have done is essentially calculated the eigenvector corresponding to lambda 1 equal to minus 2. So let us do the same exercise for V2. Okay, which will correspond to lambda, the second eigenvalue, which is minus 3. Okay, so consequently, A minus lambda 2 identity times V2. Let's figure out what it is. Okay. So if you calculate this, once again, let me do it one more time just to convey the concept. A is minus 2, 1, 0 and minus 3. And minus 3 times I will get us minus 3, 0, 0 and minus 2. Okay. And now let us say we have the two components as V21 and V22. Okay. And this is going to be the 0 vector. So what will we get if we do the subtraction? You'll see that you get 1, 1, 0 and right? V21, V22 is equal to the vector 0 and. So now we have a very odd scenario, right? Isn't it? So we have a matrix whose first row is 1, right? And the second row is completely 0. So if you do the matrix multiplication, what we are going to get is that like we are only going to get V21 plus V22 is equal to 0. That's it. Next, so essentially, the second equation, we get 0 equals 0, right? If you multiply the second row with the column vector. So this implies that V22 is equal to minus V21. Okay, so we are only going to get a relationship like this between the two components of the second eigenvector. So let's say if V21 is some C, okay, some scalar C, which is a real number, which is non-zero, then we can immediately see that V22 is going to be minus C, okay, minus V21, which is going to be equal to minus. Okay, so this implies that the second eigen vector, okay, is going to be the span of the vector 1 and minus 1. Why are we writing like this? Because we can see that this can be written as some C multiplied by minus 1, 1 and minus 1, right? So C is a non-zero here. Okay, so that's how we get the second eigenvector, okay, corresponding to this form. All right. So in fact, if I hope this calculation is clear, right? How we got the two eigenvectors. All right. So in fact, like for second order systems, we draw what is called as a phase portrait. What do I mean by the phase portrait? Let me draw it and illustrate to you. So let us say we have two state variables, x1 and x2, and our the origin is the equilibrium state. So now what happens is that like if we want to draw the two directions of the two eigenvector, right? 1, 0 is a horizontal line, okay, all right, and if you look at 1 and minus 1, it is this line, okay. The direction of 1 and minus 1 is an angle of minus 1, okay. So these are the two eigenvectors, okay, the direction of the two eigenvectors, and since both are stable, so what we do is like typically we put an arrow going towards the going towards the equilibrium state, just to indicate that both the eigenvectors are stable. Are corresponding to stable eigenvectors. Okay, so you will see that the arrows will point towards the equilibrium state, which in this case is the origin. So what it means is that like the two eigenvalues, minus 2 and minus 3, are stable eigenvalues. So that is why we put the direction of the corresponding eigenvectors, okay, when we draw what is called as a phase portrait, as something which will lead towards the equilibrium state. Okay, so this is what is called as a phase portrait. Okay, so this is what is called as a phase portrait, because like we are essentially going to have the two eigenvectors, right? So going towards the equilibrium state. So in fact, if we have any arbitrary initial state, let's say x0, so what will happen is that like it will come and then go to the equilibrium state. Okay, so because we have an asymptotically stable equilibrium state, right? So any non-zero initial state, okay, which is away from the equilibrium state, will then go to the okay. So that's the phase portrait, okay, of the system. Okay, so I hope it is clear how we calculate the equilibrium state, all right, and then like we essentially look at the what to say the stability of the equilibrium state by looking at the um, the eigenvalue, okay, of the state matrix, and then we also look at the eigenvectors corresponding to the eigenvalues, right? So and then draw the phase portrait. So that's what we do. All right. Okay. So this is one example. So let me do another example, and just to clarify these concepts. Once again, please stop me whenever there is a question. Okay, so I'm just going ahead with this example, the second example, wherein we once again consider a second order system. The state matrix, let's say, -2, 1, 0, 1. Okay. So you can see that the difference between the previous state matrix and this state matrix is that the column in the second row and the second column intersection, I have changed it from -3 to +1. Okay, so that's what we have done. So we follow the same steps, okay, to calculate the equilibrium state. We solve AX star equals 0. So which will essentially give us -2, 1, 0 and 1, x1 star and x2 star to be equal to 0 and 0. So from here, once again, if we multiply the matrix and the vector, we are going to get -2 x1 star plus x2 star is equal to 0, and then x2 star is equal to 0. So those are the two equations we will get. So immediately we will see that the equilibrium state itself is going to be the origin. Okay. Once again, we could have directly written it without calculating it because the matrix A is invertible. Okay, we know that it's going to have a unique equilibrium at the origin. But anyway, I just wanted to do the explicit calculation to show that the unique equilibrium state is the origin. So the next step is to calculate the eigenvalues so that like we can figure out we can comment on the stability of the equilibrium state. So we solve determinant of A minus lambda I equal to 0. So in this particular case, we need to solve determinant of -2 minus lambda 1, 0, 1 minus. That's equal to, this is the scalar, right? So if we calculate this, what we are going to get? We are going to get -2 minus lambda times 1 minus lambda is equal to 0. So this will imply that lambda is going to be equal to -2 and 1. Now what can we comment about the stability of the equilibrium state? We observe that one of the eigenvalues of the state matrix is now +1, which is in the right of complex plane. Okay, so immediately we can conclude that the equilibrium state is unstable. All right, so that's what we can conclude. So by following a similar process, let's calculate the two eigenvalues associated with the two eigenvectors. So let's say first we take the eigenvalue of -2. Okay, and so we want to calculate A minus lambda 1 identity times V1 equal to 0. Okay, so we want to solve this equation. So of course, I am directly going to write A minus lambda 1 9. We have done the step many times. So we just subtract, we just add 2 to the diagonal elements, right? So essentially, because we are going to subtract -2. So minus of -2 becomes +2, but that is added only to the diagonal terms, right? So we get 0, 1, 0, 3 as A minus lambda 1 I, and that's going to be equal to. So from here, what we get is V1 to 0. how do we get V12 to be 0? Because if we have this equation, if we multiply, the first equation will give us V12 equals 0. The second equation will give us V12 equals 0. So this basically implies that V12 is equal to 0. So just like the same time thing like before. So the first component V11 can now be any scalar which is not 0, right? That is the result. So consequently, first eigenvector is the span of 1, 0. Okay, which is nothing but some constant C, non-zero constant, multiplying the column vector 1. Okay, so that is the result. Okay, so as far as the first eigenvector is concerned. So similarly, let's derive the second eigenvector. So this corresponds to lambda 2 equal to 1. So now we are going to derive A minus lambda 2 identity V2 to be equal to 0. So this will give us, now in the subtract 1, right, from the diagonal element. So we will get minus 3, 1, 0 and 0. Okay, times V2 1. Okay, and V2. Okay, those are the two components of V2. Okay, so 0. So if we multiply this, we are essentially going to get minus 3V11 minus 3V21 plus V22 is equal to 0. That's it, right? Because the second element will be second row. If you multiply, we are going to get 0 equals 0. So as a result, V22 is going to be equal to 3 times V21. And let V21 be equal to some C. Okay, which is some real scalar which is non-zero. Okay, so this implies that V22 is equal to 3 times. Okay, so that's what we will have. So consequently, the second eigenvector V2 is going to be the span of 1, 1 and 3. Okay, which is nothing but some real scalar, non-zero scalar multiplying 1 and 3. Okay, so that's what we have derived, right? So that's it, right? Because the first component is of the form C, some scalar C. The second component is 3 times C, right? So that's what we have derived, right? So consequently, we will get it in this form. Okay. So we can immediately see that this is our second eigenvector. And if we draw the corresponding phase portrait, okay, so once again, this is a second order system. So drawing the phase portrait, what do we get? So let me draw this and illustrate what happens here. So this is x1, this is x2, this is the origin. Okay. So if we draw the first eigenvector, so that's going to be the horizontal axis once again, right? The second eigenvector is going to be 1 and 3, so it is going to be this direction. Okay. So now, if we want to draw the arrows, please note that on the first eigenvector, I will draw the arrow pointing to the equilibrium state. Why? Because the corresponding eigenvalue is -2, which corresponds to a stable eigenvalue, right? But on the other hand, the second eigenvector, I will draw the arrows pointing away from the equilibrium state. Why? Because now the second eigenvalue is +1, right? Which corresponds to an unstable eigenvalue, right? Or an unstable mode. So consequently, if we have any non-zero initial state, what will happen is that it will blow away to infinity along this second eigenvector. Okay, so that's what will most likely happen. Okay, so if you're not on the horizontal axis for any arbitrary initial state, ultimately as time tends to infinity, the state trajectory, okay, is going to go away from the origin along the eigenvector corresponding to V2. All right, along the direction of the eigenvector V2. All right. So that is the eigenvector corresponding to the unstable eigenvalue, which is +1. All right. So that is the phase portrait in this particular for this particular example. Fine. Okay. So this is how we calculate the equilibrium state, and we essentially calculate the eigenvalues, comment on the stability of the equilibrium state, and also draw the phase portrait. Okay. So to summarize, in today's class, we have learned the definition of stability in the sense of Lyapunov. We have essentially learned the definition. We have learned the criteria for linear time unit systems, and we have applied it for a couple of examples. All right. So I will stop today's discussion at this point, and then we will continue from here tomorrow. So are there any questions?
No, sir.
Okay. So yeah, then let me stop recording, and then we'll continue.